Welcome to my lecture on section 14.2, the gas laws. Those of you who love math will love the gas laws. In this section, we're going to talk about the relationships of temperature, pressure, volume, and I might mention moles of the gas as well. We're going to use the combined gas law to solve problems. So gas laws are mathematical. All gas laws can be described by mathematics. Gas behavior can be predicted by this theory. We can use mathematical equations to talk about change for any of the variables that we have discussed. You need to know the theory, you need to know the math. Robert Boyle. Robert Boyle was a rich Irish guy. You need to be rich to study science in the olden days. He became interested in medicine, the science of Galileo, and he studied chemistry. He was a blah, 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 blah history guy. So Boyle's law is gas pressure is inversely proportional to volume. So let's take a look at what that means. Pressure times volume is constant. And this is Boyle's law. This is the law you need to know. If you know three of those variables, you can find the fourth variable. Please note that T is constant and moles is constant. Here's a visual representation. If I have a container like I see on the left, my number of particles is the same in each of these. If I decrease the volume, if I halve the volume, I will double the pressure. The pressure will be doubled because the particles will be striking the sides of the container with twice the frequency. And this is assuming pressure is held constant. Since this is an indirect or inverse relationship, please note the shape of the curve. And please note that we've got volume on our x-axis. We have pressure. This happens to be inches of mercury on the right column. So that's Boyle's law. Says pressure is inverse to volume. And as pressure goes up, volume goes down. Or as volume goes up, pressure goes down. This is an example problem in your book. I'm not going to spend too much time on it. I'm simply going to note that we have 3 sig figs, 3 sig figs, 3 sig figs, and we can have 3 sig figs in our final answer. There are 2 ways to do this. You can either sub then solve, or you can rearrange, then sub and solve, whatever you prefer. Whatever you prefer is good with me. Our second law is Charles' law. Charles was the French physicist. He was a balloon guy, and he got interested in gases. So he had a hydrogen-filled balloon, which is a good thing they were careful. Think Hindenburg. Charles' law tells us that the volume of a fixed mass of gas, so fixed moles, is directly proportional to Kelvin temperature. So this is a direct relationship. This is a fun law, and if I had all the time in the world, we'd do this. If we extrapolate Charles' law down to 0, we get to 0 Kelvin. So that's just sort of a fun fact. That's one of the reasons we call the Kelvin scale an absolute scale. Here's the law. There should be an equal sign right there. I don't know why it's not. Let me go back. So there should be an equal sign right here. I want to make a note on this. Be careful. And don't solve for 1 over t. I get a lot of people who solve for 1 over t. I have a lot of people who say cross multiplying, but I don't know, cross multiplying is like a made up math thing, so I like to think in terms of actual math. can't read what the top of this says. Converting something to I can't read what that says. I don't know how to read that. Gas law problems always involving temperature always require Kelvin. Converting Celsius to Kelvin. So remember, you don't use a degree sign. Everybody's got their pet peeves. Dr. and Cotton and I each hate degree sign with Kelvin. There'll never be a zero volume, since we will never reach this. And to get to Kelvin, we simply add 273. Some of you might feel like using 273.15. You can use whatever you want. I'm probably do more of this than I do of this. But if you ever have results that don't match me exactly, check to see if I use 273.15. Okay, obviously if you need to go to Celsius, you take Kelvin, subtract 273. Here's an example problem, and you'll notice that both these temperatures are given to two significant figures, but when I add my 273, I end up with legitimately 3 sig figs, so my answer can have 3 sig figs. So just be careful when you're doing your work with this. This example is one that you should have worked already. Then we have Gay-Lussac. He's next. This guy's a French chemist. Physical properties of gases, another balloon guy. And his law relates pressure and Kelvin temperature. And pressure and temperature are directly proportional if the volume remains constant. I don't like that this one is in black, but it is what it is. So P1 over T1 equals P2 over T2. I'll sort of draw over this so you can see it better. So think about a pressure cooker, and I'm a big fan of pressure cookers. How does that affect the time needed to cook food? So if I make water boil under pressure, that means that the temperature will literally get hotter. And I'll demo that when I get back. These all go together to form the combined gas law, which gives us the P1 V1 over T1 equals P2 V2 over T2. This is on the back of your periodic table, and you can derive every gas law from this. So take a look at this. If temperature remains constant, the temperatures go away. If temperature remains constant, we have Boyle's law. So all you have to do is cross off the temperatures or ignore the temperatures on the combined gas law, and you can get Boyle's law. If pressure is constant, let's get the pressure terms out of there. Oh, look, now we have Charles's law. So if I say at constant pressure, just ignore pressure. Now let's do volume. Oh, there's Gay-Lussac's law. Now I want to go back. This is all I'm going to do here. There's another, I'm trying to get back a little, there we go. There's another form we use sometimes, I think I have, where I have moles inserted here. And this, if I don't talk about moles, you don't have to consider moles. So you don't have to worry about moles unless I specifically say I'm doubling the number of moles or I'm giving you some information about moles. So you can leave this out. Leave N out. Unless the problem specifically mentions change of moles. Okay, now you have a packet that you should be picking up today, that you should have picked up today, and you should do all of the combined gas law problems and all of the other problems that go with that. Please make sure your SR2QRs for this unit are done. I don't know, I might not have enough planned here today, so there's a possibility I might do the ideal gas laws next. Those calculations are a little bit more challenging, but this should be enough to get you a good start for the day.